cybersecurity, people often talk about prevention as if the perfect goal is to stop every bad thing from ever happening. In operational technology, OT, prevention is important, but resilience is just as important because the environment must keep serving real-world needs even when things go wrong. Resilience is the ability to continue operating safely through stress, disruption, and recovery without turning a manageable incident into a dangerous situation. For brand new learners, it helps to think of resilience as a design mindset rather than a single feature. It is the idea that systems should be built to endure problems, to avoid single points of failure, to stay available when components fail, and to recover in a controlled way when the unexpected happens. In this lesson, we will focus on 4 practical resilience concepts that show up constantly in OT: endurance, redundancy, high availability, and recoverability. These concepts are connected, but they are not identical, and understanding the differences helps you design systems that remain safe and trustworthy under pressure. The point is not to create a system that never fails, but to create a system that fails gracefully and can be restored confidently. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Endurance is the ability to keep operating under strain, and it often means designing so that temporary disruptions do not immediately cause unsafe outcomes or full shutdowns. In an OT environment, strain can come from many sources. A network link goes down, a server becomes overloaded, a monitoring feed becomes unreliable, a security event forces you to isolate part of the network, or a vendor connection is temporarily unavailable. Endurance asks whether the process can continue safely when normal convenience is removed. For example, if a site loses connectivity to a central operations center, can the local team still monitor and control the process using local systems and procedures? If a historian server fails, can operators still see the critical process indicators they need to run safely? If a remote access tool is disabled as a security precaution, can maintenance still proceed safely through an alternative path, even if it is slower? For beginners, the key is that endurance often lives in the operational plan as much as in the technology. It includes clear procedures for degraded operation, training for manual workarounds, and an understanding of which functions are essential versus merely helpful. A resilient design supports the people who have to operate during stress, not just the machines. Redundancy is the concept of having more than one of something so that if one component fails, another can take over. That sounds simple, but in OT it must be carefully designed because redundancy can add complexity, and complexity can create new failure modes if not managed well. Redundancy can apply to network paths, power supplies, critical servers, communication links, and sometimes even control components, depending on the process. A beginner mistake is to think redundancy is only about buying duplicates, when the real question is whether the redundant component is independent enough to survive the same failure. If the primary and backup systems share a single power source, then a power failure still takes both down. If 2 network paths share the same conduit and are cut by the same physical event, then the redundancy is only on paper. In cybersecurity terms, redundancy also has to consider shared vulnerabilities. If a single software update can crash both primary and backup because they are identical and updated at the same time, the redundancy does not help. Good redundancy design tries to avoid common mode failures, meaning failures that hit multiple components at once. In OT, preventing common mode failures is one of the most important resilience goals because it is what keeps a localized issue from becoming a full site event. High availability is related to redundancy, but it emphasizes continuous service and quick failover so that users experience little or no interruption. High availability is not only about having backups. It is about having systems arranged so that the transition from one component to another happens automatically or with minimal delay. In OT, high availability often applies to systems that operators depend on continuously, such as control system servers, operator interface systems, and critical communication services. The value of high availability is that it reduces the time window where operators lack visibility or control, which can be a safety issue. However, high availability designs must also be evaluated for security, because always-on systems can create always-on pathways for attackers if access controls and segmentation are weak. For beginners, it is important to recognize that high availability is a trade-off. It can improve safety and continuity, but it can also increase complexity and the number of moving parts. Complexity can create configuration drift, patching challenges, and monitoring gaps. That is why high availability must be paired with disciplined management, knowing which node is active, tracking changes across nodes, and ensuring that security controls apply consistently. High availability is most effective when it is deliberate and thoroughly tested, not assumed. Recoverability is the ability to restore systems and trust after an incident, and it is where resilience becomes a disciplined process rather than just a design diagram. In OT, recoverability is not only about bringing systems back online. It is about proving that they are correct and safe to use. That might mean restoring from backups, but it also means verifying configurations, validating controller logic, confirming that safety functions behave as intended, and ensuring that monitoring reflects reality. Beginners often think recovery is simply rebooting or reinstalling, but in OT, recovery must include integrity verification because operating with incorrect logic or false readings can be worse than operating with reduced capability. Recoverability also includes planning for how long recovery will take and what the process will look like when resources are limited. For example, do you have the documentation needed to rebuild a server or reconfigure a network device? Do you have offline copies of essential software and licenses? Do you have a way to authenticate when central identity services are down? These details matter because incident recovery often happens under stress, and missing prerequisites can turn a planned recovery into improvisation. Recoverability is about making sure the path back to safe operation is known, prepared, and practiced. A practical way to connect these concepts is to think about resilience as a sequence. Endurance buys you time. Redundancy prevents immediate collapse. High availability minimizes interruption, and recoverability restores full capability and trust. Endurance means you can keep operating safely while you assess and respond. Redundancy means a single failure does not immediately remove a critical function. High availability means the handoff between redundant components is fast and predictable. Recoverability means that if multiple layers fail, or if you must deliberately take systems down to contain a threat, you can rebuild and verify them without unacceptable risk. In a cybersecurity context, this sequence matters because security events often force difficult decisions like isolating networks, disabling remote access, or taking servers offline. If the system is designed with resilience, those decisions are less likely to cause unsafe outcomes. If the system is fragile, the organization may hesitate to take protective action because the operational cost feels too high. That hesitation can give attackers more time and freedom. So resilience design is a security enabler. It gives you safe options under pressure. It is also important for beginners to understand that operational resilience is not only a technical engineering problem. It is also an organizational and procedural problem. A plant can have redundant servers, but if no one knows how to switch to the backup, redundancy will not help when stress arrives. A system can support high availability, but if change control is sloppy, the backup might be misconfigured and fail when needed. A backup can exist, but if it has never been tested, you do not really know if you can recover. In OT, testing must be done carefully, but it still must be done because assumptions are dangerous. Documentation is another overlooked piece. If recovery depends on tribal knowledge held by one person, that is a resilience risk. Training is also a resilience control. Operators and engineers should know what degraded operation looks like and which actions are safe during an incident. For beginners, the key takeaway is that resilience is a system of systems, combining technology, people, and process. You cannot buy resilience as a single product, but you can design and practice it. Security and resilience also interact in a subtle way. Some security controls can reduce resilience if they are deployed without operational awareness, while some resilience designs can create security risks if they are deployed without security awareness. For example, Adding multiple remote access pathways for redundancy might improve availability, but increase the attack surface if governance is weak. Keeping a backup system permanently connected to the same network might make failover easier, but also expose the backup to the same ransomware or intrusion that affects the primary. A recovery plan that depends on cloud services might be fast, but it may fail if connectivity is disrupted or if accounts are compromised. The resilient choice is often the one that reduces common dependencies and creates safe, controlled pathways. Beginners should learn to ask two questions together. Does this design keep operations safe when something fails? And does it create new pathways for attackers or new single points of failure? When those questions are asked together, security and resilience stop being competing goals and start being co-designed. This is one of the most important OT lessons because it reflects real-world constraints. Another concept that helps connect resilience to everyday decisions is the idea of critical functions versus supporting functions. Critical functions are the ones that, if lost, create immediate safety risk or immediate process collapse, such as essential control, essential monitoring, and essential protective functions. Supporting functions are valuable but not always essential in the short term, such as advanced analytics dashboards, non-critical reporting, or convenience data feeds. Resilience design begins by identifying what is truly critical and then ensuring those functions have the strongest endurance, redundancy, availability, and recoverability. Beginners sometimes want to make everything highly available, but that can be expensive, complex, and unnecessary. A better approach is to prioritize. For example, you might prioritize local operator visibility and control because those are safety critical, while accepting that corporate reporting might be delayed during an incident. You might prioritize the ability to run the process in a stable, steady state, even if optimization features are offline. This prioritization is not about lowering standards. It is about focusing resources where physical consequences are highest. In OT, good resilience is targeted resilience. Recoverability deserves special emphasis because it often determines how long an incident truly lasts, and in many organizations, recovery is the most painful part. A system might be contained quickly, but if rebuilding takes weeks, the operational and financial impact is still severe. Good recoverability includes knowing what good looks like after restoration, which in OT includes functional correctness, not just power-on status. That may require comparing configurations to known good baselines, validating controller logic against approved versions, and ensuring that safety and alarm functions operate properly. It also includes the ability to rebuild supporting infrastructure like time synchronization, authentication services, and monitoring systems, because those enable trustworthy operation. Beginners should also understand that recovery is often constrained by vendor support, specialized expertise, and maintenance windows. That is why planning matters. If you depend on a vendor to restore a key system, you need to know how quickly they can respond and what access they will need. Recoverability is as much about reducing uncertainty as it is about restoring capability. When you can prove systems are correct, you can resume operations with confidence. In the end, designing for operational resilience means building an environment that can absorb shocks without becoming unsafe, and that can return to normal through a controlled, verifiable process. Endurance helps you keep operating safely while you assess and respond. Redundancy reduces the chance that one failure takes away a critical function. High availability makes transitions fast and predictable so operators do not lose visibility or control when components fail. Recoverability ensures you can rebuild and verify systems and trust after an incident, rather than guessing and hoping. For brand new learners, the most useful mindset is to imagine stress scenarios and ask what the system would do, what the people would do, and how you would prove it is safe. Resilience is not only about surviving attacks. It is also about surviving mistakes, software failures, vendor outages, and unexpected physical events. When you design with resilience in mind, security actions become easier because you have safe options, and operations become safer because failure does not automatically mean disaster. That is why resilience belongs at the center of OT security thinking. It is how you protect not just systems, but the real-world services and safety they support.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.